the fluid stays still, it doesn't fall out. We'll see why. Okay? So, now if I pull one end. Now Satya, in this video we are going to look at part 2 of mechanical properties of fluids. In last video we have discussed basic definition, Pascal's law application, streamline flow, equation of continuity and hydrostatic paradox. Now let us look at one of the most important concepts of this chapter, Bernoulli's theorem. It is based on streamlined flow, as this theorem is applicable only for streamlined flow and equation of continuity. Now, what does this state? When a fluid passes, when a non-viscous, incompressible and when a non-viscous incompressible fluid travels from one point to another, the total mechanical energy of the fluid remains constant. Okay? Now, what does this statement mean? What does the statement mechanical energy remains constant? Now, P plus half rho V square plus rho G H is equal to constant. This is the formula for Bernoulli's theorem. Imagine we have a pipe with varying cross-sectional area A1 and A2. Okay? Fluid of mass delta M enters and exits as per law of conservation of mass. Now, if a fluid moves from here to here, there will be some amount of work done. Similarly, here too, there will be some amount of work done. Let this be W2, let this be W1. Now, what is W1? Force into displacement. Work done is equal to force into displacement. Now, displacement is equal to velocity into time. Okay? So, work done is equal to, and what is force? Force is equal to pressure into area. Let this be P1, A1, V1. Okay? Then what will be work done? P1 into A1 into V1 into delta T. And similarly, W2 will be P2 into A2 into V2 into delta T. Okay? Now, velocity into time is just displacement or distance or height. Now, area into height will result in volume. So, work done is equal, W1 is equal to P1 into volume. And similarly for W2, W2 is equal to P2 into volume. Now, let us keep that diagram aside and look at what we have derived. W1 is equal to P1 into delta V, where delta V is volume and P1 is pressure. Now, work done to W2 is equal to negative P2 into delta V. Now, why negative? Let us look at this case. Now, fluid is entering, so there is a right side force and right side direction. But here, while fluid is moving from this point to this point, what will happen? Pressure acts in all direction. So, let us consider this force acting here and displacement here. It is moving here, and this is acting against it. So, you will get V1 into delta T, where this V is velocity. You will get in right side direction, but force into displacement. Here, displacement is this. But what is force? Negative force. Okay? So you will get negative P2 into delta V. Now, you have understood how this negative sign came. Negative, we are considering this opposite force of the fluid as fluid pushes against what is pushing it, okay? We have seen thrust, right, against the containers. Similarly, it is pushing against the fluid, acting on it. Now, if it's against, it's a negative sign. Now, what is work done? Work done is equal to energy. Now, work done total is equal to total energy, where W1 plus W2 is equal to half mv square delta m, as delta m enters and delta m exits, plus delta m g into h. Okay. Now these are at different heights, right? These are at different heights. So we'll consider this as h1 and this as h2. Okay. Now work done net is equal to W1 P1 delta V plus of minus P2 delta V is equal to half into delta mv square plus delta m into g into what is net h. Here it will be V2 minus V1, V2 square minus V1 square, and here it will be H2 minus H1. So what will you get? Here taking delta V common, P1 minus P2 is equal to half delta M into V2 square minus V1 square plus delta M into G into H2 minus H1. So here we have stated that when the speed of the fluid increases, the pressure drops. Okay? Imagine this is the wing of an aeroplane. Now, there's a streamlined flow. Okay? This kind of streamlined flow here. Now, the wind flowing is too much fast, too fast. Okay? So there will be low pressure. And here it will be slower compared to this one. Okay? So this is low pressure. This is low pressure. The above one is low pressure. Low pressure, and here it is high pressure. Okay? Now, what do we know about pressure? High pressure to low pressure, there will be a movement of high pressure to low pressure. So this pressure will move upwards, create an upward force which will lift the wing, helping the aeroplane to fly. Okay? So, what does Bernoulli's theorem state? Again, let us revise. Pressure energy, kinetic energy and potential energy remains constant throughout the fluid. Okay? Now, if there is higher speed, pressure would be low, and if lower speeds, the pressure would be generally high. Now, high pressure to low pressure movement will be there, which will create an upward lift. Upward lift means you will fly off. Okay? Let us look at application of Bernoulli's theorem. Now, speed of efflux. What is efflux? Efflux means outflow. Okay? A fluid is moving out, right? So the speed of the fluid which is moving out. Now, imagine we have a container, open container, filled with fluid till height Y2. Now, there is pressure of atmospheric pressure acting on it, and there is a hole at height h or height Y2. Okay, height Y2 with pressure of atmospheric pressure acting on it. There is A2 and A1. Note that A1 is more and more greater than A2. Okay, so now what is equation of continuity? A1 V1 equal to A2 V2. Am I right? Am I right? A1 V1 is equal to A2 V2. Now, V1, that is the velocity of the fluid here, is equal to A2 by A1 into V2. Okay? Now, V1, we know that A2 is smaller, very, very small compared to A1. So, you will get result. It as V1 is approximately 0. Because if imagine you have 1 centimeter of 1 centimeter square of A2 and 100 meter square of A1. So what will you get? You will get a very small value, which will approximate it to 0. Okay? Now, V1 is equal to 0, P1 is equal to PA, P2 is also equal to PA. Okay? Now, what is, as per Bernoulli's theorem, P1 plus half rho V1 square plus half rho G plus rho GH is equal to P2 plus half rho V2 square plus rho GH 2. Okay? Now, we know that P1 and P2 are same. Now, half rho V1 square, you will get rho V1 square as 0. Now, half rho V2 square is equal to rho GH, rho G H1 minus H2. Now, what will be the velocity V2? V2 square is equal to rho G H1 minus H2 into 2 by rho. So, V2 square is equal to 2G and H1 minus H2. This height minus fluid height till here will give you H, capital H, okay, which till where the fluid will flow, and after this point the hole will fall above the fluid, okay. So fluid can't generally beat gravity and come out, okay. So capital H. Now V2 is equal to root 2GH. So we have found the speed of the outflow from this hole here, which is root 2GH. Okay? Let us look what happened here. V1 is 0. Pressure 1 is, the container is open, so pressure of atmospheric pressure. P2 is also atmospheric pressure. So as per Bernoulli's theorem, P1 plus half rho V1 square plus rho GH is equal to P2 plus half rho V2 square plus rho GH2. Now we know that P1 and P2 will get cancelled out. Half rho into 0, V1 is 0, so totally this term will be 0. Now rho GH1 minus rho GH2 will result in half rho V2 square. Okay? We'll take rho G common, so H1 minus H2. We will get one capital height H. So V2 square is equal to rho G H1 minus H2 into 2 by rho. Now rho will get cancelled. G H1 minus H2, G capital H, 2GH. So V2 is equal to root 2GH. Okay. Now, students, let us take a tube, U-shaped tube, to understand what are the concepts of atmospheric pressure. Now imagine I have a tube, okay, filled with the fluid. Now they are the same height. Am I right? They are the same height. So now if I pull one end above, okay, if I pull this, what will happen? They come again at the same height. And if another end, same thing happens and they come at the same height. So we are going to see why that happens, and when we close this end with the thumb and I leave it to free fall, the fluid stays still, it doesn't fall out. We'll see why, okay? Now what did we see in the previous clip, okay? We took a tube, we moved it up and down. Now when we moved it up and down, even though no matter at what height the other tube was, we got the same fluid height. Am I right? We got the same fluid height. Why? Then look, atmosphere has pressure. The atmosphere we live in has pressure. So in this tube there was 10 now atmospheric pressure. In this tube also there was atmospheric pressure acting. So no matter what vertical motion you bring in, it will be the same 10 power pressure of atmosphere now, which is equal to 10 power 5 pascals almost. So it would balance it out. So there would be no extra push force. There would be same equal force. Okay. Now, in case 2, why not the liquid falling? Okay. Imagine there was this setup, okay? I covered this part of the tube by my thumb. What happened? The fluid stayed till here only. Okay? It did not flow out. Why? There is trapped air, okay? There is trapped air which has pressure. But there is no atmospheric pressure. PA, pressure of atmosphere, is not there. And here there is pressure of atmosphere. Now, this is equivalent to a baby elephant pushing or baby elephant stomping, okay? So, it does not allow the fluid to move out and it pushes against the fluid. Now, ever when you travel in an aeroplane, buy a chips bag, okay? The chips bag when you are at the airport would look like this, a bit of uninflated, but when the altitude increases, when you go on a mountain and stuff, or go in the skies, what happens? Altitude increases, that means pressure drops. When pressure drops, high pressure, this would become high pressure. So high pressure would move to low pressure. Am I right? So there would be a bulge or an inflated effect, okay, in the chips. And why do people have ear pains in aeroplane? The same phenomenon. Why? Inside your body there is almost equivalent to 10 power 5 pascals atmospheric pressure, and as you go above and above, or in the mountains or flying in the skies, what will happen? The eardrums, okay? The eardrums would carry inside high pressure. High pressure would move to low pressure, which would create an bulge or swelling effect, which would lead to pop sound and pain, okay? Now moving on, how do you measure this atmospheric pressure? Now let us look at how we use devices to measure atmospheric pressure. First one is mercury barometer, okay? Mercury barometer. Now, Torricelli was a curious person. Everyone believed that atmosphere does not have any weight, so it does not give any pressure. But he was curious. He knew, or he felt that there is pressure of atmosphere. So what he did is, he took a tube, okay? First he took a tube. He filled it totally with mercury, okay? He filled it totally with mercury, and then he inverted it in the mercury by holding the top, and then he inverted it. Now, he noticed that there is some amount of vacuum created, called Torricelli vacuum. There was vacuum created in this tube. Now, If there is vacuum, there will be pressure equal to 0. So as per pressure's formula, pressure inside is equal to pressure outside, as there is same fluid containing. So P inside is equal to P outside. P outside is just pressure of atmosphere. P inside is pressure of vacuum plus pressure of the mercury column. Okay, mercury column. Now, pressure of atmosphere is equal to, as there is vacuum, so there won't be any pressure. So this will be 0 plus pressure of mercury column will be rho of mercury, gravity and height. PA is equal to rho GH. Now PA is equal to, there is, what is the density of mercury? Density of mercury is 13.6 into 10 power 3 kilogram per meter cube. Okay. Height, he measured the height to be at 76 centimeter. Okay, when he inverted it, the mercury's height was still 76 centimeter. Now, after that, the gravity is equal to 9.8 meter per second. So what is the pressure of atmosphere? PA is equal to rho 13.6 into 10 power 3 kilogram per meter cube into gravity 9.8 into height is in centimeter, converting it to meters, 0.76, which would result in pressure of atmosphere is equal to 1.013 into 10 power 5 pascals. Okay, approximately 1.013 into 10 power 5 pascals. Okay, one device he used is mercury barometer. Now what is mercury barometer? He inverted a tube containing mercury into a mercury basin or whatever, mercury container. Okay, the height of the mercury column was still 76 centimeter. There was vacuum above it. So pressure created in the vacuum column is 0, and outside pressure must be equal to pressure inside. So pressure of atmosphere is equal to pressure of volume, pressure of vacuum plus pressure of mercury column, and we know that pressure is equal to rho GH. So PA is equal to rho GH. Pressure of atmosphere is equal to 1.013 into 10 power 5 pascals. Okay. What was another device used? It was manometer. Okay, let us look at what that was. So let us move on to look at what an open tube manometer is. Now, there is one open end and one closed end. Okay, one closed end with a flask kind of thing filled with gas. Okay, PG. Let the pressure of gas be PG. Now there are three cases in this conditions. First one is PA greater than PG. Second is PA less than PG. And third is PA equal to PG. Now in the tube case, we see the experiment. We have seen the experiment of the tube. What happened? PA is equal to PA in that one. Now, when PA is equal to PG, what will happen? The liquid column will stay at same height. When PA is less than PG, the PG would push the fluid, which will create increment of height in the right side. And PA greater than PG, PA would push and PG would be less. So the fluid pushed by PG will have an increment in height in left side. Okay. Now when PA is greater than PG, okay, when pressure of atmosphere is greater than PG, PG is equal to PA minus rho GH, the water column's height minus pressure of atmosphere will give you pressure of gas. And in second case, what will happen in second case? Pressure of gas is equal to pressure of atmosphere plus rho GH When PA is less than PG, so there will be this height column and atmosphere also. So when both are acting, this gas is acting against them. So when total pressure is equal to pressure of atmosphere plus rho GH. When PA is equal to PG, PA equal to PG, what will happen? Then there will be no difference in height, so we can't use rho GH formula, as H will be same 0. Here H is the difference of height. In both cases H is the difference of height, but here there will be height difference 0, so K is equal to PG. Okay.